How's it going, ladies and gentlemen? Mr. Donnie here, taking a look at Chapter 14 problems, looking at 14.1 and 2, factors affecting reaction rates and reaction rates. Let's start with number 1. It says, why will a burning splint burn more strongly in pure oxygen than in air? All right, well, let's think about this. Oxygen acts as a catalyst? No. Oxygen is a reactant. So it is definitely not a catalyst. It gets used up. Oxygen is a product. That's wrong. Nitrogen is an inhibitor, so reacting with pure oxygen where there is less nitrogen will speed up the reaction. Makes sense, but that's not why. That's wrong. Oxygen is a reactant in combustion, and the concentration of oxygen is higher in pure oxygen than it is in air. So basically we're saying if we were to increase the concentration of O2, it's going to speed up the reaction. All right, number 2. Which of the following are not valid units for reaction rate? So rate, we have to take a look at change over time. So there needs to be a time factor here. So A, we got moles per second. That would work. B, we got molar per second. That would also work. Mole per hour. That would work. Moles per liter. That would not work because there's no change over time. There's no time in that one. So that one wouldn't work. Moles over liter hour. Well, that would work because we have that moles per liter, which is really molar per hour. That would also work. So D would have to be our final answer. 3. Nitrogen dioxide decomposes to nitric oxide and oxygen as illustrated in the following reaction. During a reaction at 190 degrees Celsius, NO2 drops from 0.0100 to 0.00550 molar in 100 seconds. All right, the rate of disappearance for this period is blank. So we want the rate of disappearance. So rate is going to be the change over time. So the change is going to be the difference between 0.100 and 0.00550 all over the time, which is 100 seconds. And we get, 4.5 times 10 to the negative 5th molar per second. Right? Just plugged and chugged. 4. Express the reaction rate in terms of change in molarities for each of the molecules involved over time. All right, so here you can see we have 4 NH3, 7 O2, 4 NO2, and 6 H2O. So if we're trying to express the reaction rate in terms of these components, we got to remember it's the change in whatever it is. So if we're looking at an NH3, it's the change in NH3 divided by 4 because its coefficient is 4. So the reaction rate would just be 1/4 of that. For O2, it would be the change in O2 over 7 because the coefficient is 7. For NO2, again, it would be the change in NO2 over its coefficient of 4. And for H2O, again, it would be change in H2O over 6 because that is its coefficient. Take a look at number 5. Rate of disappearance of HBr in the reaction below. Alright, so I always circle whatever they're talking about. Is 0.0601 molar per second at 250 Celsius. The rate of appearance of H2, hey, something new, so I'm going to circle that a different way, is blank. Alright, so we got to look at the coefficients, a 2-to-1 ratio. So the rates are going to follow the same pattern of 2-to-1. So we got 2-to-1 is 0.601 to blank. And the reason I know where to put the 0.601 is because it's of the HBr, which is the 2. So now I can do some cross multiplying and dividing, solve for x, and I get x equals 0.3005 molar per second. 6. The rate of appearance of H2 in the gas phase of the reaction is 0.30 molar per second at 350 Celsius. The rate of reaction is blank. All right, this is kind of a trick question. Now, the coefficient in front of H2 is 1, so its reaction rate is the same thing. Now, if this was the reaction rate for HBr, then we'd have to divide it by 2 because of the coefficient of 2 there. But since H2 has a coefficient of 1, you don't have to change anything. Combustion of ethylene is represented by the reaction below. When the disappearance rate of O2 is 0.46 molar per second, the rate of appearance of H2O is blank. Alright, so I'm going to have to take a look at the coefficients. So it's a 3 to 2 ratio between O2 and H2O. And this 0.46 is of O2, so I got to put it on O2 side. Now, the 3 is saying for every 3 O2s you use up, you're making 2 H2Os. So the rates are going to follow that proportion as well. So now it's a matter of cross multiplying and dividing. And you get X equals 0.31 molar per second. Alright, cool. Hope you found that helpful. Bring questions to class. I'll see you there.